They say Stonehenge was built by simple farmers, but the evidence says otherwise. Stones hauled across oceans and mountains, precision without maps, burials from distant lands, knowledge passed without writing. Generations returning for 2,000 years. Who organized it? Who controlled it? Why was this place never abandoned? The ground is full of answers and contradictions. Every measurement raises new doubts. Every discovery erases an old explanation. And the deeper researchers dig, the more impossible this monument becomes. The first records in chalk and ink. Stonehenge stands on Salisbury Plain in Wiltshire, southern England, on land that slopes gently toward the River Avon. Its setting is open and wind-exposed, with shallow chalk soils and long sightlines. The monument sits within a wider prehistoric landscape that includes burial mounds, earthworks, and ancient trackways. Modern roads and fields cut through the area, but many features remain mapped and dated through excavation and survey. The stone circle and its surrounding earthwork have been examined in stages over more than 400 years. Some of the earliest written descriptions that survive in detail come from the 1600s, when antiquarians began to measure and sketch what they saw. Those early observers did not work with modern excavation methods, yet their notes preserve details that later changed through collapse, repair, and restoration. Stones that stood upright in one century fell in another. Some were re-erected in the 1900s after engineering work, and their positions are now fixed in concrete beneath the turf. A measurable ground plan of Stonehenge was produced in 1740 by William Stukely, an English antiquarian who visited repeatedly and recorded the site with careful drawings and commentary. Stukely's plan captured the arrangement of the visible stones and the surrounding bank and ditch. His writing also reflects the religious interpretations common among scholars of his time, but his drawings remain valuable for the simple reason that they show stones before later collapses and restorations altered the view. Earlier still, John Aubrey, writing in the 1660s, described Stonehenge and identified a ring of depressions around the monument. These are now called the Aubrey Holes. They are a circle of pits inside the bank, later confirmed by excavation. Their presence mattered because they indicated that the monument was more than a stone circle. It had phases, including elements that were not made of stone or were removed long before modern visitors arrived. The first large-scale excavations began in the early 1900s, after a series of stone falls and concerns about stability. A lintel and uprights collapsed in 1900, and in 1901, the engineer William Gowland carried out excavations while undertaking restoration. Gowland recorded his work in detail, including the construction of stone holes and the packing materials used to secure uprights. His observations, made while the ground was open, provided direct evidence of how some of the larger stones had been set in place. Between 1919 and 1926, Lieutenant Colonel William Hawley directed excavations at Stonehenge that expanded the record considerably. Hawley's work helped define the site's ditch, bank, and internal features, and his reports contributed to the idea of multiple building stages. Later researchers refined the sequence, but the general point remained consistent. The monument did not appear as a complete stone ring in a single moment. It accumulated, adjusted, and reworked across centuries. Radiocarbon dating, developed in the mid-20th century, changed how Stonehenge was described in scientific terms. By the 1950s and 1960s, archaeologists could place key phases into approximate calendar ranges. The earliest major construction is now typically assigned to the late Neolithic, around 3000 BC, when the circular ditch and bank were made. The Aubrey Holes belong to this early stage. The large sarsen stones, which form the best-known ring and the central trilithons, are generally dated to later in the Neolithic, around 2500 BC, based on associated material and stratigraphy from excavations. Additional rearrangements and activity continued into the Bronze Age. The stones themselves are of more than one type. The largest blocks, the sarsens, are a hard silcrete sandstone used for the outer circle and many of the prominent structural elements. Smaller stones, often called blue stones because they can appear bluish when wet or freshly broken, include several rock types, such as dolerite and rhyolite. These bluestones are smaller than the sarsen's but still substantial. Their presence has been documented through standing stones and through stone fragments and sockets within the monument. Identifying stone sources has become an important part of the modern record. Geological work has linked many bluestones to outcrops in the Preseli Hills of West Wales, including areas such as Carn Godog and Craig Rosy Felin, based on petrographic and geochemical matching in studies published in the 2010s. For the sarsens, a major study published in 2020 used geochemical analysis to suggest that most of the sarsen stones at Stonehenge came from West Woods, near Marlborough in Wiltshire, roughly 25 kilometres to the north. These findings did not depend on legend or tradition. They used the measurable properties of rock to tie the monument to specific landscapes. Archaeological fieldwork around Stonehenge has also affected how its builders are described in concrete terms. Excavations at Durrington Walls, about 3 kilometres northeast of Stonehenge, revealed a large late Neolithic settlement, with house floors, middens, and evidence of feasting. The site has been investigated by teams including Mike Parker, Pearson, and colleagues in the 2000s and 2010s. Dating places significant activity there around the same general period as the major stone settings at Stonehenge. The material remains include animal bones, pottery, and tools consistent with late Neolithic communities in southern Britain. Human burials in the broader region add another layer of dated evidence. The Amesbury Archer, found near Amesbury and dated to around 2400–2200 BC, was buried with a notable assemblage that included copper knives and gold ornaments. Isotopic analysis suggested that he spent part of his early life outside Britain, likely in continental Europe. This burial does not identify who built Stonehenge in a simple way, but it documents that people, objects, and ideas moved across long distances during the period when the monument's stone architecture was being set and used. The public understanding of Stonehenge also changed through legal and institutional events. In 1882, it was protected under the Ancient Monuments Protection Act, one of the early British efforts to safeguard archaeological sites. Ownership and management shifted over time, and in the 20th century the surrounding landscape became a focus of conservation. In 1986, Stonehenge, Avebury, and associated sites were inscribed as a UNESCO World Heritage Site, recognizing the wider concentration of monuments in the region, not only the standing stones. Through all of this, one feature stays constant in the record. Stonehenge is not isolated in time or in terrain. The ditch and bank, the pits, the stone sockets, the tool marks, and the repaired uprights exist as physical traces that can be measured and compared. Antiquarian sketches, early restoration notes, and modern laboratory results all sit in the same archive of observation. Dates cluster in the late Neolithic and early Bronze Age. The builders appear in the evidence as communities capable of quarrying, shaping, transporting, and erecting heavy stone, while maintaining a landscape of settlements, ceremonies, and burial practices across southern Britain. The paths, pits, and temporary settlements. The ground surrounding Stonehenge extends outward in gentle rises and shallow valleys, shaped by chalk bedrock and thin soils. Rain drains quickly through this surface, leaving few permanent streams beyond the River Avon to the east. In prehistoric times, this landscape supported open grassland, mixed with patches of woodland. Pollen records taken from nearby sediment cores indicate that tree cover declined gradually during the Neolithic period, suggesting sustained human activity. By around 3000 BC, much of the plain had become semi-open terrain, suitable for grazing and movement. Within this setting, archaeologists have documented a network of earthworks, pits, and linear features that date to the same general period as Stonehenge. These elements do not form a single planned system. Instead, they accumulated through repeated use. Some were dug, filled, reopened, and altered over generations. Their overlapping dates reflect continued occupation and modification, rather than a brief episode of construction. One of the most prominent features is the Stonehenge cursus, a long earthwork running east to west north of the monument. It measures approximately 3 kilometres in length and consists of parallel banks and ditches. Excavations conducted in the mid-20th century and later radiocarbon dating suggest that it was built around 3500 BC, several centuries before the main stone settings. Its purpose remains uncertain. but its orientation and scale indicate organized labor and coordinated planning. The cursus intersects with later monuments, showing that earlier features remained visible and influential in later phases. Closer to Stonehenge itself, numerous pits and post holes have been recorded. Some of these appear beneath or near later stone settings. Others lie scattered across the surrounding plain. Excavations led by Richard Atkinson in the 1950s and 1960s documented many such features, though later surveys using geophysical methods expanded the mapped record. Magnetometry and ground-penetrating radar revealed additional buried anomalies consistent with pits, hearths, and compacted surfaces. These features indicate repeated temporary occupation rather than dense permanent settlement. Few substantial house structures have been identified immediately adjacent to Stonehenge. Instead, activity appears to have concentrated in specific zones, with people gathering, working, and dispersing according to seasonal or ceremonial patterns. Soil chemistry studies show localized concentrations of phosphate and organic material, consistent with food preparation and waste disposal in certain areas. Durrington Walls provides a clearer picture of residential activity. Located near the River Avon, the site includes a large henge enclosure and traces of timber structures. Excavations from 2003 onward revealed clusters of house floors, hearths, and refuse pits. The houses were small, roughly square or rectangular, with clay floors and central fireplaces. Pottery fragments and animal bones suggest short-term occupation rather than long-term habitation. Radiocarbon dates place most of this activity around 2000, 600 2000, 500 BC. The distribution of animal remains at Durrington Walls shows a pattern dominated by pigs and cattle. Many of the animals were slaughtered at young ages, and cut marks indicate systematic butchery. Isotopic analysis of teeth suggests that some animals were brought from distant regions, including Wales and northern England. This implies that people travelled to the area with livestock, possibly for periodic gatherings. These events left behind concentrated deposits rather than continuous settlement layers. Between Durrington Walls and Stonehenge runs the River Avon. Along its banks, archaeologists have identified ceremonial and practical features. One of the most notable is the Avenue, a pair of parallel banks and ditches that link Stonehenge to the river. The avenue curves gently across the landscape and aligns with specific solar events at certain points. Excavations have shown that it was constructed in stages, beginning around 2500 BC. Its surface was compacted through repeated use, forming a durable route. Along the Avon itself, wooden posts and platforms have been found at sites such as Bluestone Henge, a now vanished stone circle near the riverbank. Excavations in 2008 revealed stone sockets arranged in a circular pattern, later filled and covered. Radiocarbon dates indicate that this structure was dismantled around the same time that major rearrangements occurred at Stonehenge. The relationship between these sites is documented through stratigraphy and artifact distribution rather than written records. Transport across the landscape left few direct traces, but indirect evidence is present. Repeated movement along certain corridors, compacted soil, and altered vegetation patterns. Micromorphological studies of sediments along the avenue and nearby routes show layers of trampled chalk and organic debris. These layers differ from undisturbed soils nearby, indicating sustained foot traffic. Similar evidence has been found along parts of the riverbank. Stoneworking also affected the terrain. Although no large quarry exists directly on Salisbury Plain for sarsen stone, smaller fragments and working debris have been identified. Some sarsens were likely shaped near their final positions. Hammerstones made of flint and other hard materials have been recovered from excavation contexts. These tools show wear patterns consistent with repeated impact against stone surfaces. Flint extraction and processing occurred at several locations in the wider region. Chalk uplands contain natural flint nodules, which were mined in shallow pits and shafts. Evidence from sites such as Easton Down and other parts of Wiltshire shows that Neolithic communities dug vertical shafts and horizontal galleries to reach high-quality flint. The resulting tools were used for woodworking, hide preparation, and stone shaping. These activities supported construction and daily life, but did not leave large permanent structures. Burial monuments also shaped movement. Round barrows and long barrows dot the plain, many predating or overlapping with Stonehenge's main phases. These earth mounds served as visual markers. Excavations of barrows in the 19th and 20th centuries revealed human remains, grave goods, and layered construction episodes. Their placement suggests deliberate positioning along ridges, routes, and sightlines. People moving across the plain would have encountered these features regularly. Seasonal patterns are suggested by the archaeological record. Faunal remains indicate slaughter peaks in winter and early spring. Pollen and insect evidence from midden deposits support periods of concentrated activity followed by quieter intervals. This rhythm implies that large groups gathered at certain times rather than living continuously near Stonehenge. The landscape functioned as a meeting ground rather than a permanent village. Survey work in the early 21st century expanded understanding of this pattern. The Stonehenge Hidden Landscapes Project, using radar and magnetometry, identified dozens of previously unknown features, including large pits and circular arrangements. Some pits, over 10 meters in diameter, form a rough ring several kilometers from Stonehenge. Radiocarbon dates suggest late Neolithic origins. Their function remains unclear, but their scale indicates coordinated excavation efforts. Taken together, these findings describe a working landscape rather than a single construction site. Paths, pits, enclosures, and temporary dwellings formed a shifting network. Activities were distributed across space and time. Stonehenge occupied a central position within this network, but it depended on surrounding zones for labor, resources, and social gatherings. The evidence does not point to a single moment of concentrated building. Instead, it records repeated episodes of movement, assembly, and dispersal across several centuries, the stones and their distant origins. Across the open ground of Salisbury Plain, the stones at Stonehenge appear uniform from a distance, yet close examination shows clear differences in size, texture, and composition. These differences reflect distinct geological histories rather than decorative choice. Long before the monument took shape, the materials that define it were formed in separate environments, under different conditions, and at widely separated locations. Modern study has focused on tracing these materials back to their points of origin, using measurable physical properties. Sarsen stone makes up the largest and most visually dominant elements of Stonehenge. These blocks are composed of tightly cemented sand grains bound by silica, giving them exceptional hardness and durability. Sarsens occur naturally across parts of southern England, often as scattered boulders lying at or just below the surface. Their distribution is irregular, shaped by erosion rather than organized quarrying in later historical periods. The sarsens at Stonehenge form the outer ring and the central trilithons. Individual uprights can weigh more than 25 metric tons, with some estimates reaching closer to 30 tons depending on density. The lintels that span the uprights were shaped to curve gently, creating a continuous circular line. Examination of these stones reveals deliberate working, including flattened faces and carefully cut joints. Mortise and tenon connections and tongue and groove joints were carved directly into the stone, a technique documented through detailed survey and laser scanning. Determining where these sarsens came from remained unresolved for many decades. Early suggestions favored areas closest to the monument, based largely on convenience. In 2020, a comprehensive geochemical analysis, led by David Nash, provided clearer evidence. By comparing trace element signatures from Stonehenge sarsens with samples taken from known sarsen spreads, researchers identified a strong match with stones from West Woods, near Marlborough in Wiltshire. This area lies roughly 25 kilometres north of Stonehenge. West Woods contains dense concentrations of sarsen blocks, many partially embedded in the ground. Surveys have recorded clusters of stones similar in size and composition to those used at Stonehenge. While no deep quarry pits have been identified, shallow hollows and disturbed ground suggest that stones were extracted from the surface or from shallow deposits. This method would be consistent with Neolithic practices, which relied on leverage and gradual removal rather than deep excavation. The smaller stones at Stonehenge, commonly referred to as bluestones, differ markedly from the sarsens. They include a range of igneous and volcanic rock types, most notably spotted dolerite. Other identified materials include rhyolite, volcanic tuff, and ash. These stones typically weigh between 2 and 4 tons and fracture differently under impact, leaving distinct tool marks. Petrological studies in the 20th century first suggested that many bluestones originated in West Wales. Subsequent work refined this conclusion. Detailed mineral analysis linked several Stonehenge bluestones to specific outcrops in the Preseli Hills of Pembrokeshire. Sites such as Carn Godog and Craig Rosy Felin show close matches in mineral composition and texture. Research published between 2011 and 2019 strengthened these links through systematic sampling and comparison. Excavations at these Welsh sites revealed features consistent with prehistoric stone extraction. At Craig Rosy Felin, elongated stone pillars appear to have been detached from natural rock faces and positioned nearby. At Carn Godog, recesses and broken edges indicate deliberate removal of stone columns. Charcoal recovered from associated sediments provided radiocarbon dates centering on the late 4th and early 3rd millennia BC. These dates overlap with early phases of activity at Stonehenge, but precede the erection of the large Sarsen circle. This temporal gap suggests that bluestone extraction did not occur solely in response to the final monument layout. Instead, stone removal in Preseli may have been part of earlier or parallel activities, with stones transported, stored, or reused over extended periods. The movement of bluestones from West Wales to southern England represents a substantial logistical effort. The straight-line distance exceeds 200 kilometres, crossing varied terrain and multiple river systems. No direct physical evidence of transport equipment has been found. As a result, interpretations rely on landscape analysis, experimental reconstruction, and indirect archaeological indicators. River transport has been proposed as one component of this movement. From the Welsh coast, stones could have been loaded onto simple watercraft and moved along the Bristol Channel, then inland via rivers such as the Avon. Prehistoric use of waterways is well documented elsewhere in Britain through logboats and riverine settlements. Along the Avon near Stonehenge, evidence of repeated activity supports the idea that the river played a role in movement and access. Overland transport remains equally plausible. Experimental archaeology has shown that groups using wooden sledges, rollers, and rope can move multi-ton stones across prepared ground. Chalk surfaces, when dampened, reduce friction. Microscopic analysis of compacted chalk layers along the Stonehenge Avenue indicates repeated heavy traffic, consistent with dragging or hauling loads rather than casual foot movement. Within the monument, bluestones were not fixed in a single arrangement. Excavation records show numerous sockets and packing features that do not correspond to the stone's current positions. Some bluestones were removed and reset, while others were broken and reused as smaller elements. This pattern was documented during early 20th century excavations and confirmed by later stratigraphic studies. Certain bluestones exhibit signs of dressing and reshaping. Tool marks suggest trimming rather than full surface finishing. Compared with Sarsens, bluestones were modified more selectively, possibly to fit changing layouts. Fragments recovered from pits and fills indicate that breakage occurred during handling or reconfiguration. The Sarsens also show evidence of staged preparation. While rough shaping may have occurred near their source, finer adjustments were made at Stonehenge itself. Hammerstones recovered from the site show wear patterns consistent with prolonged use against hard stone. Debris fragments found in stone holes and surrounding layers support on-site working. Erecting the stones required controlled excavation and stabilization. Stone holes were dug with sloping sides and flat bases. After a stone was raised into position, the remaining space was packed with chalk rubble, clay, and smaller stones. This method is documented in excavation notes from William Gowland and later investigators. The packing layers differ from natural deposits, confirming deliberate placement. Lintel placement involved additional steps. Earthen ramps and wooden supports likely allowed lintels to be slid upward and maneuvered into position. Weathering patterns on the upper surfaces suggest long-term exposure with minimal displacement after erection, aside from recorded collapses in the historical period. No contemporary written records describe these processes. All reconstructions depend on physical traces preserved in stone, soil, and surrounding features. The consistency of working techniques across different stones indicates shared knowledge rather than isolated improvisation. This knowledge was maintained across generations, as suggested by repeated construction phases using similar methods. The stones at Stonehenge thus record more than architectural form. Their mineral composition preserves information about distant landscapes. Their surfaces carry marks of extraction, transport, and adjustment. Together, these characteristics document sustained interaction between regions separated by considerable distance. The monument's fabric reflects movement across Britain rather than reliance on a single local resource, tools, labour, and technical knowledge. The physical traces left at Stonehenge include more than stone and earth. Scattered throughout excavated layers are tools, fragments, and modified surfaces that record how work was carried out. These materials provide direct evidence of the technical practices used during construction and maintenance. They also reflect how labour was organised over long periods without written instruction or centralised administration. Most tools associated with Stonehenge are made of flint, a material widely available in the chalk landscapes of southern Britain. Flint nodules occur naturally within chalk deposits and were extracted through shallow digging and mining. At several sites in Wiltshire, including Easton Down and Durrington Walls, archaeologists have documented Neolithic flint mines with vertical shafts and horizontal galleries. Radiocarbon dates indicate that some of these mines were active between 4000 and 2500 BC. Flint tools recovered near Stonehenge include hammerstones, scrapers, knives, and cores. Hammerstones were typically rounded or oval nodules selected for their hardness. Many show battered edges and crushed surfaces caused by repeated impact. Microscopic wear analysis indicates use against stone, wood, and compacted soil. Some hammerstones were likely used to shape sarsens and bluestones, while others served in earthwork construction. Scrapers and knives were produced by striking flakes from prepared cores. Their presence suggests that construction work involved a wide range of supporting activities, including tool maintenance, clothing production, and material preparation. Flint debris found in working areas indicates on-site tool manufacture and repair. Antler picks represent another important category of tools. These were made primarily from red deer antlers, shaped into pointed digging implements. Excavations of the Stonehenge ditch and other earthworks recovered numerous antler picks embedded in construction layers. Radiocarbon dating of these picks places many between 3000 and 2500 BC. Their distribution corresponds closely with major digging episodes. Wear patterns on antler picks show abrasion and breakage consistent with heavy use in chalk soils. Some picks were discarded after breaking, while others were reshaped and reused. The repeated presence of such tools indicates organized digging operations rather than casual excavation. Their standardized form suggests shared methods of manufacture and use. Wooden tools and structures are less well preserved due to soil conditions. However, indirect evidence supports extensive wood use. Post holes, stake impressions, and compacted surfaces indicate temporary frames, ramps, and platforms. At Durrington Walls, preserved house floors and post settings demonstrate routine timber construction. Similar techniques were likely employed at Stonehenge for scaffolding and lifting systems. Charcoal fragments recovered from hearths and pits provide information about fuel and woodworking. Analysis shows frequent use of oak, hazel, and ash. These species are suitable for construction and toolmaking. Their presence reflects managed woodland exploitation rather than random collection. Pollen records support sustained clearance and regrowth cycles during the Neolithic. Labour organisation can be inferred from spatial patterns in the archaeological record. Excavations reveal clusters of working debris near stone settings and earthworks. These clusters include flint flakes, broken tools, and packing materials. Their concentration suggests designated work areas rather than scattered individual activity. At Durrington Walls, refuse deposits contain large quantities of animal bone and pottery associated with communal meals. Radiocarbon dates place these deposits around 2600, 2500 BC. The scale of these middens implies gatherings involving hundreds of people. Such gatherings likely coincided with major construction or reorganization phases at Stonehenge. Analysis of pig and cattle remains shows standardized butchery practices. Some animals were slaughtered at distant locations and transported partially processed, while others were killed on site. Isotopic studies show that livestock came from multiple regions, suggesting participation by groups from across Britain. Housing evidence at Durrington Walls suggests temporary accommodation for workers. Houses were small, with thin walls and simple hearths. Many appear to have been occupied briefly before abandonment. Repeated rebuilding in the same area indicates periodic reuse rather than permanent settlement. This pattern supports the interpretation of seasonal labor gatherings. Human remains also contribute to understanding labor and health. Skeletal material from nearby burial sites shows evidence of physical stress. Some individuals exhibit joint degeneration, muscle attachment enlargement, and healed fractures consistent with heavy manual work. Dental wear and dietary isotopes indicate diets rich in meat and cereals, compatible with intensive activity periods. No single burial assemblage identifies specialized craftsmen. Instead, tools and skeletal evidence suggest that many individuals participated in multiple tasks. Skills were likely learned through observation and repetition rather than formal training. The consistency of techniques across generations implies stable transmission of practical knowledge. Stone shaping required precise control. Examination of sarsen surfaces shows pecking, grinding, and smoothing marks. These were produced using hammerstones and abrasive materials such as sand and water. The uniformity of joint shapes across different trilithons indicates standardized measurement practices, even in the absence of written units. Experimental archaeology has reproduced several of these techniques. Replicas of antler picks and flint hammers have been used to dig chalk and dress stone. These experiments confirm that Neolithic tools were sufficient for large-scale construction when applied systematically. They also demonstrate that repeated maintenance of tools was necessary to sustain work. Raising stones required coordinated movement. Stone holes show sloping sides that facilitated controlled lowering and lifting. Packing layers reveal repeated adjustments during erection. Some holes contain multiple packing phases, indicating repositioning after initial placement. This suggests careful monitoring rather than irreversible placement. Rope and binding materials are not preserved, but indirect evidence exists. Impressions in soil and wear on stone edges suggest the use of fibrous cords. Likely materials include plant fibers such as flax and animal sinew. Textile fragments from other Neolithic sites confirm that such materials were available and widely used. Leadership and coordination are difficult to identify directly. No administrative buildings or symbolic authority markers have been found. Instead, organization appears to have operated through shared customs and cooperative routines. The repetition of construction methods across centuries implies continuity of practice rather than episodic improvisation. Weather and seasonal constraints also shaped labor patterns. Chalk soils become softer when damp, facilitating digging and hauling. Faunal and botanical evidence suggests peaks of activity in winter and early spring. These periods coincide with lower agricultural demands, allowing larger groups to assemble. Repair and maintenance work continued long after initial construction. Historical records document collapses and repairs in the medieval and early modern periods. But prehistoric repairs are also visible. Some stones were repacked, re-leveled, or adjusted before final arrangements were completed. These interventions are visible in stratigraphic sequences. The absence of metal tools during most construction phases is significant. Copper and bronze objects appear in Britain after about 2500 BC, overlapping with later Stonehenge activity. However, most major stonework predates widespread metal use. The monument therefore reflects a technology based almost entirely on stone, bone, wood, and fiber. Knowledge was embedded in routine practice. Tool forms, working surfaces, and construction sequences indicate learned patterns repeated across projects. Similar methods appear at other henge and stone circle sites, suggesting regional traditions. These traditions were adaptable, but retained core principles. The combined evidence portrays construction as an ongoing social process rather than a single project. Tools were produced, worn, repaired, and discarded. Workers assembled periodically, shared meals, and returned to their home regions. Technical knowledge circulated through participation rather than formal instruction. The monument's durability depends on these cumulative efforts. Each phase built upon earlier work, reusing tools, modifying structures, and refining techniques. The resulting architecture reflects long-term collaboration rather than isolated achievement. Timekeeping, observation, and spatial alignment. Stonehenge is positioned within a landscape where natural horizons, seasonal light patterns, and long sightlines are clearly visible. The surrounding terrain contains few steep elevations, allowing observers to track the movement of the sun and moon across much of the year. This openness made the area suitable for repeated visual observation of rising and setting points. Archaeological surveys and historical measurements show that several structural elements at Stonehenge correspond to consistent astronomical positions. The most frequently documented alignment is associated with the summer solstice sunrise and the winter solstice sunset. From the center of the monument, the sun rises over the heelstone on or near the longest day of the year. This relationship was noted in antiquarian writings as early as the 18th century and measured more precisely in the 19th and 20th centuries. William Stukeley recorded the alignment in the 1720s, and later surveyors confirmed it using calibrated instruments. The heelstone stands outside the main circle to the northeast. It is a single sarsen block set upright in a shallow socket. Excavations have shown that its current position corresponds closely with earlier placement, though minor adjustments may have occurred. Soil layers around its base indicate multiple phases of packing and stabilization. Radiocarbon dates from nearby features suggest placement during the later Neolithic. Opposite the heelstone, the southwest axis aligns with the winter solstice sunset. From within the central trilithons, the setting sun appears between paired uprights at this time of year. Survey data, collected in the 20th century by Gerald Hawkins and later by Clive Ruggles, confirmed this orientation within narrow margins of error. These measurements account for changes in Earth's axial tilt and horizon profile over millennia. The main axis of Stonehenge runs northeast to southwest. This axis is reflected not only in the stone arrangement but also in the avenue, which extends from the monument toward the River Avon. The avenue follows a curved path but maintains a general alignment consistent with solstitial events. Excavation has shown that its banks and ditches were modified over time, yet its orientation remained stable. Beyond the solstitial axis, other stones and features display secondary alignments. Certain bluestone settings correspond to lunar standstill positions, when the moon reaches extreme rising and setting points over an 18-6-year cycle. The 4 station stones, located near the perimeter of the monument, form a rectangle that approximates lunar alignment geometry. These stones are now incomplete, but excavation records document their original positions. Early recognition of possible lunar connections appeared in the work of Norman Lockyer in the early 20th century. Later researchers approached the issue using statistical methods to distinguish intentional alignments from random placement. Studies conducted in the 1970s and 1980s concluded that some lunar-related orientations were plausible, though not all proposed examples met strict probability thresholds. The Aubrey Holes, a circle of pits inside the main bank, have also been considered in relation to timekeeping. There are 56 holes, documented by John Aubrey in the 17th century and confirmed through excavation. Some researchers suggested that this number relates to lunar cycles. However, excavations indicate that the holes were filled and reopened multiple times, complicating any fixed numerical interpretation. Radiocarbon dating places their initial digging around 3000 BC. Stone placement accuracy reflects careful measurement. Survey analysis shows that many stones are positioned with consistent spacing and angular relationships. The outer sarsen circle forms a near-perfect ring, with deviations of only a few centimeters in some sections. This level of precision implies repeated checking and adjustment during construction. No measuring devices have been recovered. However, indirect evidence suggests the use of cords, stakes, and sightlines. Circular layouts could be produced using fixed central points and rotating cords. Peg holes and compacted chalk surfaces near stone sockets support this method. Similar techniques are documented ethnographically and experimentally. Shadow behavior also provides information about spatial planning. At certain times of year, shadows cast by uprights fall across specific interior stones. Photographic records from the 20th century document these patterns. While shadows shift gradually over centuries due to axial precession, reconstructed models indicate that these effects were more pronounced during the Neolithic. The surrounding landscape contains additional aligned features. The Stonehenge cursus includes terminals that align with solstitial sunrise and sunset when viewed from certain positions. Excavations at these terminals revealed pits and deposits dated to the late 4th millennium BC. Their placement suggests that horizon observation was established in the area before the main stone circle was erected. Barrows and other burial monuments also follow patterned orientations. Many round barrows in the region are aligned along ridgelines or sightlines connected to prominent solar points. Survey mapping shows clustering of these monuments along routes and visual corridors linked to Stonehenge. These patterns developed over centuries and were maintained through successive building phases. Seasonal gatherings at Durrington Walls coincide with solstitial periods. Faunal remains indicate winter slaughter peaks, aligning with midwinter activity. Radiocarbon dates from midden deposits support concentrated use around these times. This correspondence suggests that observation and social gathering were interconnected rather than separate practices. Recording time did not require permanent markers. Changes in daylight length, shadow direction, and horizon positions provided regular reference points. Repeated observation over generations would allow communities to predict seasonal transitions. Stonehenge's architecture formalized these observations within a durable setting. Astronomical knowledge at Stonehenge was embedded in construction rather than inscription. No symbolic representations of celestial bodies have been found at the site. Instead, orientation, spacing, and placement served as the primary means of recording patterns. This approach differs from later written calendars, but achieves functional regularity. Maintenance of alignment required periodic correction. Excavations reveal episodes of stone resetting and repacking. Some stones were slightly repositioned after initial erection. These adjustments may reflect responses to subsidence, weathering, or observational refinement. The continued use of the same axis suggests intentional preservation of orientation. Long-term changes in Earth's rotation and tilt gradually altered observed positions. Modern calculations show that solstitial points have shifted slightly since 2500 BC. Despite this drift, Stonehenge's primary alignments remain broadly effective, indicating initial placement within narrow tolerances. Observational practices at Stonehenge were not isolated. Similar alignments appear at sites such as Callanish in Scotland and Maeshowe in Orkney. These parallels suggest shared traditions of horizon-based measurement across Neolithic Britain. Stonehenge represents one regional expression within this wider pattern. The physical evidence supports sustained attention to spatial order and cyclical time. Stones were positioned with reference to repeatable natural events. Routes, enclosures, and surrounding monuments reinforced these orientations. Over many generations, these arrangements were preserved, modified, and reused. Timekeeping at Stonehenge relied on visible regularity rather than abstract notation. Light, shadow, and horizon movement provided continuous reference. The monument's form integrated these elements into a stable framework. Through this integration, seasonal change became embedded in the physical landscape, ritual activity, and material deposits. Across the chalk plain and within the monument enclosure, archaeologists have identified layers of material that reflect repeated acts of placement, removal, and burial. These materials include animal bones, pottery fragments, worked stone, charcoal, and human remains. Their distribution and dating indicate that ceremonial and commemorative activity occurred alongside construction and maintenance over many centuries. The evidence is preserved in pits, ditches, stone holes, and secondary fills. One of the earliest forms of ritual deposition appears in the ditch surrounding the central enclosure. Excavations conducted by William Hawley and later by Richard Atkinson recorded concentrations of animal bone and antler within primary and secondary ditch fills. Radiocarbon dating places many of these deposits in the late 4th and early 3rd millennia BC. The materials were not randomly scattered, they were placed in specific sections of the ditch, often in association with antler picks used during excavation. Antler picks recovered from these contexts sometimes show little wear, suggesting they were deposited shortly after use. Some were placed carefully rather than discarded. This pattern has been interpreted as deliberate deposition rather than waste disposal. Similar practices have been observed at other Neolithic monuments, where tools used in construction were later buried within the structures they helped create. Animal remains form one of the largest categories of ritual material. Excavations inside and around the monument have recovered bones from cattle, pigs, sheep, and deer. At Durrington Walls and other nearby sites, pig bones dominate, particularly from animals slaughtered at young ages. Cut marks and breakage patterns indicate systematic processing for consumption. However, selected bones were placed in pits and ditches rather than disposed of with general refuse. Some cattle skulls and limb bones were found in isolated deposits near the avenue and within enclosure features. These elements are underrepresented in domestic refuse and may reflect symbolic selection. Radiocarbon dating links many of these deposits to periods of intense activity around 2600, 2400 BC. The timing corresponds with major construction and rearrangement phases. Pottery fragments are another significant component. Most pottery belongs to late Neolithic grooved ware and early Bronze Age beaker traditions. Grooved ware vessels are characterized by thick walls and incised decoration. Beaker pottery is thinner and often decorated with geometric patterns. Both types appear in ceremonial contexts as well as domestic areas. Many pottery sherds were deposited broken rather than intact. Some pits contain groups of fragments that can be refitted, indicating that vessels were broken deliberately and placed together. At Durrington Walls, large quantities of grooved ware were recovered from middens associated with communal feasting. Smaller deposits near the monument suggest that pottery was also used in more restricted settings. Charcoal and ash layers provide evidence of controlled burning. Hearths and fire pits have been identified within settlement areas and near ceremonial features. Analysis of charcoal indicates the use of oak, hazel, and hawthorn. In some cases, charcoal was placed in pits alongside bone and pottery, forming mixed deposits. These contexts suggest structured disposal rather than accidental accumulation. Human remains represent another important category. Early phases of activity are associated with cremation burials placed in and around the Aubrey holes. Excavations in the 1920s and later reanalysis in the 2000s identified cremated bone from at least 58 individuals. Radiocarbon dates place most of these burials between 3000 and 2500 BC, making them among the earliest known cremation cemeteries in Britain. The cremated remains were often placed in small pits or containers and covered with chalk rubble. Some were accompanied by simple grave goods, such as bone pins or small pottery vessels. Others appear without associated objects. The distribution of burials within the enclosure suggests that specific areas were reserved for funerary use during early phases. Later burial practices shifted toward inhumation in nearby barrows. Round barrows constructed during the early Bronze Age contain crouched burials, often with beaker pottery, copper objects, or stone tools. These barrows cluster in the wider landscape rather than within the main enclosure. Their placement maintains visual and spatial connections with the monument. Isotopic analysis of human remains indicates varied geographic origins. Some individuals buried in the region grew up locally, while others spent childhood in distant areas, including Western Britain and continental Europe. These findings suggest that participation in ritual activities was not limited to a single community. Movement of people accompanied movement of materials and animals. Worked stone objects also appear in ritual contexts. Polished stone axes, some made from distant sources such as Cumbria and Wales, have been found in pits and ditch fills. These axes show little evidence of practical use, indicating symbolic value. Their deposition near major monuments reflects wider Neolithic traditions of placing prestigious objects in ceremonial settings. Small bluestone fragments recovered from fills and pits may also represent ritual reuse. Some pieces were deliberately shaped into tools or pendants. Others were placed unmodified. The reuse of stone from earlier settings suggests that material from the monument itself held significance beyond its structural role. Water-related deposition is visible along the River Avon. Excavations near river crossings and platforms have recovered animal bone, pottery, and worked flint. These materials were placed in slow-moving sections of the river or buried nearby. Similar practices are known from other prehistoric river sites in Britain and are associated with boundary and transition zones. Temporal patterns emerge from radiocarbon dating of deposits. Peaks in deposition occur during periods of major construction and reorganization. Between these peaks, fewer ritual deposits are present. This rhythm suggests that ceremonial activity intensified during certain phases rather than continuing uniformly. The organization of deposits reflects repeated conventions. Certain materials appear together in multiple contexts. Bone, pottery, charcoal, and tools are often combined in similar proportions. This consistency indicates shared expectations about how and where materials should be placed. These expectations were maintained over generations. Not all deposits were permanent. Some pits were reopened and modified. Earlier material was disturbed and mixed with later offerings. Stratigraphic sequences show cycles of digging, filling, and recutting. These actions suggest ongoing engagement with earlier deposits rather than abandonment. No inscriptions or symbolic carvings accompany these materials. Interpretation relies entirely on spatial relationships, dating, and comparative analysis. Similar patterns appear at other henges and ceremonial sites across Britain, including Avebury and Mount Pleasant. This broader distribution indicates that the practices observed here formed part of a wider cultural framework. Ritual activity was embedded within everyday tasks. Feasting, tool use, construction, and burial overlapped spatially and temporally. Materials moved between domestic and ceremonial contexts. This movement blurred strict divisions between practical and symbolic behavior. The deposits preserved in soil layers represent cumulative decisions made over centuries. Each placement added to an existing record. Together, these layers document changing traditions, repeated gatherings, and sustained attention to specific locations. The monument functioned as both a physical structure and a repository of material memory, population, migration, and cultural networks. Material recovered from burials, settlements, and refuse deposits in southern Britain shows that the communities active around Salisbury Plain were not geographically isolated. Chemical signatures in human remains, variations in artifact styles, and the distribution of raw materials indicate repeated movement between regions. These traces form a record of long-distance contact maintained over several centuries. They reflect patterns of travel, exchange, and social connection rather than permanent relocation alone. One of the primary methods for identifying mobility is isotopic analysis of teeth and bones. This technique measures elements such as strontium and oxygen, which vary according to local geology and water sources. Values formed during childhood remain fixed in tooth enamel. Studies conducted since the early 2000s on burials from Wiltshire show that many individuals did not spend their early years in the immediate area. The burial known as the Amesbury Archer, discovered in 2002, illustrates this pattern clearly. Radiocarbon dating places his death between approximately 2400 and 2200 BC. Analysis of his teeth indicates that he grew up in Central Europe, possibly near the Alpine region. He was buried with copper knives, gold ornaments, and stone tools. These items are consistent with connections to continental exchange networks. A second individual buried nearby, sometimes referred to as the Amesbury Companion, displayed isotopic values consistent with Western Britain. The proximity of these two graves, combined with their differing geographic signatures, demonstrates that people from distant regions were present in the same ceremonial landscape. Both burials date to the early Bronze Age, a period of increasing cultural interaction. Earlier remains also reflect mobility. Cremated bone from the Aubrey holes has been subjected to isotopic analysis using improved methods developed in the 21st century. Results suggest that some individuals originated in Western Britain, including areas consistent with Wales. These burials date to around 3000 BC, indicating that long-distance movement was present from early phases. Genetic studies provide additional information. Ancient DNA research published after 2017 shows that populations associated with Beaker pottery introduced new genetic ancestry into Britain after about 2500 BC. This ancestry is linked to groups from continental Europe. Over several centuries, these populations became dominant in much of Britain, including southern regions. This genetic change corresponds with shifts in material culture. Beaker pottery, characterized by thin walls and geometric decoration, appears in graves and settlements after 2500 BC. These vessels are associated with individual burials and metal objects. Their spread reflects both population movement and the transmission of social practices. Portable artifacts further document long-distance networks. Polished stone axes recovered near Stonehenge have been traced to quarries in Cumbria, North Wales, and Cornwall. Petrographic analysis links many to specific sources such as the Great Langdale region. Some axes show little wear, suggesting they were valued as exchange items rather than tools. Pottery styles also show wide distribution. Grooved ware, common in the late Neolithic, appears across Britain and Ireland with relatively consistent forms. This uniformity implies sustained contact between communities. Later, beaker ceramics connect Britain to Western and Central Europe through shared manufacturing techniques and decorative patterns. Metal objects represent another layer of connectivity. Copper and bronze artifacts appear in the Stonehenge region after about 2400 BC. Lead isotope analysis has traced some copper to sources in southwest Ireland and Central Europe. These materials reached southern Britain through multi-stage exchange systems rather than direct procurement. Amber beads found in early Bronze Age graves indicate even wider connections. Chemical analysis links some amber to Baltic sources. These objects travelled through multiple regions before reaching Britain. Their presence reflects participation in long-distance trade routes extending across northern Europe. Settlement evidence supports periodic gatherings of diverse populations. Excavations at Durrington Walls reveal repeated episodes of short-term occupation. Houses were built, used briefly, and abandoned. Refuse deposits indicate large communal meals. These patterns suggest seasonal aggregation involving people from different areas. Isotopic analysis of animal remains strengthens this interpretation. Pig and cattle teeth from Durrington Walls show signatures consistent with origins in Wales, northern England, and other distant regions. Transporting livestock over such distances required coordinated movement of people and resources. River systems facilitated travel and exchange. The Avon, Thames, and Severn formed interconnected corridors linking southern Britain to western and central regions. Archaeological finds along these waterways include pottery, tools, and ritual deposits. Logboats recovered from other sites confirm that river transport was technologically feasible. Overland routes also played a role. Chalk ridgeways provided relatively dry pathways across southern England. Some of these routes align with later historic trackways, indicating long-term continuity. Their proximity to monuments suggests sustained use as movement corridors. Language and social identity cannot be reconstructed directly. However, similarities in artifact forms and construction techniques imply regular communication between groups. Shared practices were maintained through repeated contact rather than sporadic encounters. No evidence points to centralized political authority controlling these networks. Instead, exchange appears to have operated through reciprocal relationships, seasonal meetings, and shared ceremonial traditions. Participation in monument-related activities likely reinforced social bonds. Burial practices reflect changing identities over time. Early cremation cemeteries emphasize collective treatment of the dead. Later inhumation graves emphasize individual status and personal possessions. This transition parallels genetic and cultural change, indicating shifts in social organization. Children buried in the region sometimes show non-local isotopic values. This suggests that entire families, not only specialists or traders, participated in long-distance movement. Migration and mobility involved multiple generations. Despite population changes, use of the monument continued. New groups adopted existing ceremonial landscapes rather than abandoning them. Construction methods, burial locations, and deposition practices were modified within established frameworks. Objects circulating through these networks accumulated layered meanings. Axes, metals, and ornaments carried histories of movement and exchange. Their placement in graves and monuments marked participation in wider systems of relationship. The archaeological record therefore reflects a landscape embedded in extensive human networks. People arrived, departed, returned, and formed new connections over centuries. Materials and ideas followed similar paths. The monument functioned within this interconnected environment. Mobility did not erase local traditions. Incoming practices blended with existing customs. Hybrid material forms and flexible social arrangements emerged through this process. The resulting culture reflects sustained interaction rather than sudden replacement. Evidence from isotopes, genetics, artifacts, and settlements demonstrates that the region formed part of a broader European context. Connections were maintained through repeated travel and shared ceremonial participation. These networks shaped how communities organized labor, exchange, and identity, memory, continuity, and long-term use. Long after the main phases of construction ended, the monument on Salisbury Plain continued to receive attention, modification, and care. Archaeological evidence shows that later communities did not treat the site as abandoned or obsolete. Instead, they returned to it repeatedly, adjusting existing features and inserting new elements into an already ancient setting. These actions left a layered record of continuity that extends from the late Neolithic into historic times. Structural modification is one of the clearest indicators of long-term use. Excavation records show that several stones were reset after initial erection. Packing material beneath uprights sometimes contains multiple layers, indicating that stones were adjusted or restabilized. These layers differ in composition and compaction, suggesting interventions separated by time rather than a single construction episode. Radiocarbon dating of organic material trapped within packing deposits supports this sequence. Bluestones provide particularly clear evidence of rearrangement. Socket patterns beneath the surface do not always correspond to the stone's current positions. Some sockets were cut, filled, and later recut. These features show that stones were removed, relocated, or replaced over extended periods. The reasons for these changes are not recorded, but the physical evidence indicates sustained engagement rather than neglect. The sarsen stones also show signs of maintenance. Several lintels exhibit reworked joint surfaces, suggesting adjustment after initial placement. Weathering patterns on some uprights differ between faces, implying rotation or repositioning. These changes likely occurred gradually as stones settled or shifted within their sockets. The effort required to correct such movement indicates that maintaining the monument's form remained important. Earthworks surrounding the stone settings also underwent modification. The enclosing ditch and bank show evidence of recutting and partial infilling. In some sections, later material overlies earlier deposits without erasing them completely. This pattern suggests periodic clearing or reshaping rather than wholesale reconstruction. Antler picks found in later ditch layers indicate continued use of traditional digging tools well after the initial phase. Burial practices illustrate another aspect of continuity. Early cremation burials placed in and around the Aubrey holes represent one of the earliest known formal cemeteries in Britain. Although cremation within the enclosure appears to have declined after the early 3rd millennium BC, burial activity continued in the surrounding landscape. Round barrows constructed during the early Bronze Age maintained visual and spatial relationships with the monument. These barrows were not randomly distributed. Many were positioned along ridges or sightlines connected to the stone circle. Excavations show that some barrows were reopened, with additional burials inserted generations after initial construction. This practice indicates that ancestral memory was actively maintained. The monument served as a reference point anchoring later funerary activity. Material deposits also document reuse. Later pottery fragments, including beaker and early Bronze Age wares, appear in fills associated with older features. These sherds were placed into existing pits, ditches, and hollows rather than entirely new contexts. Such placement suggests deliberate engagement with earlier structures, depositing material in ancient features linked present activity to the past. Metal objects provide further evidence of temporal layering. Bronze Age tools and ornaments have been recovered from contexts near the monument. These objects differ markedly from earlier Neolithic materials, yet they appear alongside older stone and bone elements. Their presence indicates that newer technologies were incorporated into existing ceremonial frameworks rather than replacing them outright. Environmental data supports continued use of the surrounding landscape. Pollen cores taken from nearby sediments show sustained open grassland conditions through the Bronze Age. Woodland clearance and grazing continued, indicating ongoing human presence. These patterns contrast with areas that show abandonment or reforestation, suggesting that the monument's setting remains socially significant. Roman period activity introduces another phase of interaction. Although the stone circle was already ancient by the time Roman influence reached Britain, archaeological finds indicate continued visitation. Coins, pottery fragments, and small offerings have been recovered from the vicinity. These objects are not associated with large-scale rebuilding but reflect episodic use. The site appears to have retained symbolic value even as cultural practices changed. Written references from the early medieval period are scarce but suggest awareness of the monument. Later folklore and place name traditions indicate that the stones remained prominent in local memory. By the early modern period, the site attracted antiquarian interest. Scholars such as John Aubrey and William Stukely documented the monument with drawings and measurements, preserving information about stone positions before later collapses. These antiquarian records themselves form part of the continuity record. Stones that fell in the 17th and 18th centuries were later re-erected using early documentation as a guide. Restoration work carried out in the 20th century relied on excavation data, photographs, and historical sketches. Concrete footings beneath several stones mark these interventions. They represent modern efforts to preserve rather than reinterpret the monument. Management of the surrounding land also reflects changing attitudes. In the 19th century, agricultural activity encroached on the site, damaging some earthworks. Protective legislation introduced in the late 19th and early 20th centuries limited this impact. The scheduling of the monument under national heritage laws formalized its status as an object of preservation. Scientific research introduced new forms of engagement. Excavations conducted by William Hawley, Richard Atkinson, and later teams recorded stratigraphy, artifacts, and construction techniques in detail. These investigations altered the physical site through digging and backfilling, but also generated a permanent documentary record. Each intervention added another layer to the monument's history. Public access further shaped long-term use. Paths, fences, and visitor facilities changed how people moved around the site. While these features are modern, their placement reflects ongoing negotiation between preservation and use. The monument remains active within contemporary cultural life, even as its prehistoric functions are studied and re-evaluated. Continuity is also visible in alignment preservation. Despite stone movement and resetting, the primary northeast-southwest axis has been maintained. Adjustments made during prehistoric and modern periods respected this orientation. This consistency suggests that spatial order retained significance long after initial construction. The persistence of attention across millennia distinguishes the site from many contemporaneous monuments that fell into disuse. Earthworks elsewhere were abandoned, eroded, or repurposed. In contrast, this monument accumulated interventions rather than being erased. Each generation engaged with what was already present. No single period dominates the record. Instead, the site reflects successive phases of care, adaptation, and reinterpretation. Tools, materials, and methods changed, but engagement continued. The monument functioned as a durable focal point rather than a finished project. Memory was embedded materially. Stones preserved earlier arrangements. Pits contained traces of prior deposits. Later additions referenced earlier forms. This layering allowed the past to remain visible and accessible. Physical continuity supported social memory without written records. The archaeological sequence demonstrates that long-term use involved both stability and change. Certain elements were preserved, while others were modified. These decisions were selective rather than uniform. Communities chose which aspects to maintain and which to alter. Through this process, the monument became a cumulative record of human action. Each phase added information rather than replacing what came before. The result is a complex palimpsest, rather than a single-purpose structure. Evidence from stratigraphy, material culture, and environmental data shows that engagement persisted for more than 2,000 years. This persistence required effort, coordination, and shared understanding. It also required recognition of the site's importance across cultural transitions. The monument's endurance reflects its capacity to absorb change while retaining identity. Physical form, spatial order, and location remained recognizable even as meanings shifted. This balance between continuity and adaptation underlies its long-term survival. The record preserved in soil and stone does not point to a fixed function. Instead, it documents repeated return. The site remained part of lived landscapes across generations. Its history is defined as much by reuse as by construction, knowledge transmission without writing. The construction and continued use of the monument required the preservation of technical and social knowledge over many generations. This knowledge was not recorded in written form. Instead, it was maintained through repeated practice, shared routines, and observable patterns embedded in the landscape. Archaeological evidence allows reconstruction of how information was passed on without texts, diagrams, or formal instruction. Repetition is one of the clearest indicators. Construction techniques visible at the site follow consistent methods across different phases. Stone holes were cut with similar profiles, using sloped sides and flat bases. Packing materials show comparable layering patterns, combining chalk rubble, smaller stones, and soil. These similarities occur even when phases are separated by centuries, indicating that later builders followed established conventions rather than inventing new ones. Tool forms also demonstrate continuity. Antler picks used in early ditch construction resemble those found in later reworking phases. Flint hammerstones recovered from different contexts show similar sizes and wear patterns. The consistency of these tools suggests that their manufacture and use followed learned standards. These standards were likely reinforced through observation and participation rather than formal teaching. Learning by doing would have been central. Younger individuals working alongside experienced members would observe techniques directly. Mistakes and corrections would be visible in the process. Evidence of recut stone holes and adjusted packing layers indicates that placement was sometimes corrected. These corrections reveal active evaluation and refinement rather than rigid adherence to an abstract plan. Spatial planning also reflects transmitted knowledge. Circular layouts, consistent spacing between stones, and alignment along fixed axes required shared understanding of geometry and orientation. The ability to reproduce these patterns implies familiarity with methods such as using chords, central points, and sight lines. These methods leave indirect traces, including peg holes and compacted surfaces, but no permanent measuring devices. The preservation of alignment across multiple construction episodes indicates intentional maintenance. When stones were reset or replaced, they were returned to positions that preserved overall spatial order. This suggests that later groups understood not only how to build but why certain arrangements mattered. Such understanding would have been communicated through tradition rather than explanation. Ritual practices further supported knowledge transmission. Depositional patterns repeat similar combinations of materials across time. Bone, pottery, charcoal, and tools appear together in comparable contexts. The recurrence of these combinations indicates shared expectations about appropriate actions. New participants would learn these conventions through involvement in ceremonies. Seasonal gatherings likely played a key role. Evidence from animal remains and settlement debris indicates periodic large-scale assemblies. During these events, knowledge could be reinforced through collective activity. Building, feasting, and ritual deposition occurred in shared settings. These gatherings created opportunities for instruction through example. Movement between regions also contributed to transmission. People arriving from other areas brought practices and techniques with them. However, the persistence of local construction styles suggests that incoming knowledge was adapted rather than replacing existing methods. This blending process required negotiation and selective adoption. Material culture served as a mnemonic system. Stone arrangements, earthworks, and pathways encoded information spatially. Returning to the same places reinforced memory. The landscape itself acted as a reference framework. Knowledge was recalled by moving through space rather than consulting records. Repair and maintenance activities reinforced learning. Adjusting stones, clearing ditches, and reworking features required recalling previous methods. These tasks would have reactivated stored knowledge. The need to match earlier work ensured continuity of technique. No evidence indicates specialized instruction sites. Instead, learning appears embedded in everyday and ceremonial labor. Tools, materials, and structures formed an open curriculum. Participation was the primary means of education. The absence of writing did not limit complexity. The monument demonstrates precise planning and long-term coordination. Knowledge persisted because it was enacted repeatedly. Each construction phase reaffirmed earlier practices. This system depended on social stability. Communities needed to value continuity and recognize authority and tradition. The willingness to preserve alignments and methods implies respect for inherited knowledge. Deviations occurred, but within accepted boundaries. Errors and variation are present. Slight differences in stone size, spacing, and finish indicate flexibility. Knowledge transmission allowed adaptation while maintaining core principles. This balance prevented stagnation without losing coherence. The archaeological record thus reflects a durable information system based on practice. Skills were not abstracted from action. They existed only when performed. This form of knowledge required active engagement to survive. The monument's longevity suggests that this system was effective. Knowledge was preserved across demographic change, migration, and technological shifts. New materials and tools were incorporated without disrupting core practices. Transmission without writing relied on visibility. Stones, pits, and paths made methods legible. Observers could infer processes from results. This visibility reduced dependence on verbal explanation. Time itself reinforced learning. Repeated cycles of activity aligned with seasons and gatherings. Regularity supported memory. Predictable rhythms made knowledge stable. The evidence shows that continuity did not require centralized control. Shared practice and collective participation were sufficient. Knowledge belonged to the group rather than individuals. This mode of transmission shaped how the monument evolved. Changes occurred incrementally. Large-scale redesign was avoided. The structure accumulated rather than transformed abruptly. Understanding this process clarifies how complex projects were sustained over centuries. The monument stands as a record of embodied knowledge, maintained through action rather than text. The absence of writing leaves no direct testimony. What remains is pattern. Consistency across time reveals how information moved forward. The record is physical rather than verbal. This continuity of practice enabled later communities to engage meaningfully with an already ancient site. Knowledge was inherited along with the stones themselves, competing explanations and scholarly limits. Interpretation of the monument has changed repeatedly as new evidence and methods became available. Early explanations relied on visible form and analogy rather than excavation. Later approaches incorporated stratigraphy, radiocarbon dating, and laboratory analysis. Each phase of research produced explanations shaped by the tools and assumptions of its time. The result is a layered, scholarly record rather than a single authoritative account. 17th and 18th century interpretations were based almost entirely on surface observation. Antiquarians described stone arrangements, measured distances, and compared the site to known classical structures. Without excavation, they inferred purpose from geometry and alignment. Their explanations often reflected contemporary intellectual frameworks rather than prehistoric conditions. These interpretations were speculative but influential, setting terms that persisted for centuries. The introduction of controlled excavation in the late 19th and early 20th centuries shifted emphasis toward physical evidence. Digging exposed stone holes, packing layers, and buried features that were invisible at the surface. This work demonstrated that the monument was constructed in stages. However, early excavations often lacked precise recording standards. Stratigraphic relationships were sometimes disturbed or incompletely documented, limiting later reanalysis. Radiocarbon dating transformed chronological understanding, but introduced its own constraints. Early dates had wide error margins and were sensitive to contamination. As calibration improved, previously accepted timelines were revised. Some phases, once thought contemporaneous, were separated by centuries. These adjustments required reinterpretation of construction sequences and social context. Geophysical survey expanded knowledge without excavation. Magnetometry and radar revealed hidden features across the surrounding landscape. These discoveries showed that the visible stones represent only part of a much larger complex. However, geophysical data require interpretation and ground truthing. Anomalies may represent multiple feature types. Without excavation, certainty remains limited. Astronomical interpretations illustrate methodological tension. Some proposed alignments were based on selective observation. Later, statistical approaches rejected many earlier claims. Even when alignments are confirmed, interpreting intent remains difficult. Orientation alone does not specify meaning. Scholars must distinguish between functional observation, symbolic reference, and incidental placement. The concept of a single builder or unified plan has been challenged by evidence for long-term modification. Earlier explanations often assumed centralized design. Stratigraphic data instead show incremental change. This complicates attribution. The monument cannot be assigned easily to one group, period, or purpose. Scholarly models must account for continuity and variation. Migration studies added biological data, but also introduced interpretive limits. Isotopic and genetic results show movement, but they do not specify motivation. Migration does not explain why particular construction decisions were made. These methods provide context rather than direct explanation. Experimental archaeology demonstrated technical feasibility but not historical certainty. Replicating stone transport or erection shows what is possible under controlled conditions. It does not prove that specific methods were used. Experimental results must be integrated cautiously with archaeological evidence. Modern explanations are constrained by preservation bias. Organic materials rarely survive. Wooden structures, ropes, and textiles are inferred rather than observed. This absence limits reconstruction of labor organization and ritual practice. Stone and bone dominate the record because they endure. Interpretive models are also shaped by disciplinary boundaries. Archaeology, geology, astronomy, and genetics contribute different perspectives. Integrating these approaches requires compromise. No single method resolves all questions. Disagreement persists not because of error alone, but because evidence supports multiple compatible explanations. Scholarly restraint reflects recognition of these limits. Recent publications emphasize description over assertion. Claims are framed probabilistically rather than conclusively. This shift reflects awareness that evidence is incomplete and unevenly distributed. The monument's complexity resists reduction. Attempts to assign a single function oversimplify the record. Construction, ritual, observation, and social gathering overlapped. Scholarly explanations increasingly acknowledge this multiplicity without resolving it into a single narrative. Interpretation remains an ongoing process. New techniques continue to refine understanding while revealing additional uncertainty. Each advance clarifies some aspects and complicates others. The scholarly record thus remains open-ended. The question of advancement and terminology. Descriptions of the communities associated with the monument often rely on modern terms that did not exist in prehistoric contexts. Words such as advanced, civilized, or complex are applied retrospectively, shaped by contemporary expectations about technology, hierarchy, and written record. Archaeology approaches these terms cautiously, using material evidence rather than abstract labels. The record from Salisbury Plain provides a basis for examining what such terminology can and cannot describe. Technological capability is one common measure of advancement. The construction of large stone structures demonstrates planning, coordination, and mechanical understanding. Quarrying, shaping, transporting, and erecting multi-ton stones required knowledge of materials and force. However, these abilities developed within a technological system based on stone, wood, bone, and fiber. Metal tools were rare or absent during most major construction phases. By modern standards, the technology appears limited, yet it was sufficient for sustained monumental building. Architectural precision is another frequently cited indicator. The outer sarsen circle forms a near-regular ring. Mortise and tenon joints and curved lintels show deliberate shaping rather than rough assembly. These features demonstrate control and repeatability. At the same time, variation in stone size, spacing, and finish indicates flexibility rather than standardized mass production. Social organization is more difficult to assess. No evidence of palaces, administrative centers, or permanent elite residences has been identified near the monument. Settlement remains suggest temporary occupation and seasonal aggregation. This pattern differs from later urban societies, but does not imply disorganization. Coordination could be achieved through kinship, shared ritual, and periodic gatherings rather than centralized authority. Population size does not appear to have been large or permanently concentrated. Excavated settlements show modest house structures and limited duration of use. Large-scale activity occurred intermittently. This challenges definitions of advancement based on density and permanence. The monument was produced by dispersed communities acting collectively over time, rather than by a single populous center. Economic specialization is another criterion often applied. Tool assemblages show functional diversity, but few artifacts indicate full-time craft specialization. Stone shaping, tool production, and food processing were likely shared tasks. Skills were distributed rather than segregated into distinct professions. This organization contrasts with later societies, but reflects effective use of available labor. Knowledge systems present a similar challenge. The monument's alignments demonstrate awareness of cyclical natural events. spatial planning required geometric understanding. These capabilities were embedded in practice rather than formal notation. Without writing or numerical records, knowledge persisted through repetition and observation. Modern definitions often equate advancement with abstract representation, yet the archaeological record shows that practical knowledge can achieve comparable outcomes. Long-distance interaction is sometimes interpreted as evidence of complexity. The movement of stone, metal, and people across Britain and beyond indicates extensive networks. These networks operated without roads, currency, or written contracts. Exchange was maintained through social relationships rather than formal institutions. This form of connectivity differs from later trade systems, but functioned reliably over centuries. Ritual and symbolic behavior complicate terminology further. Depositional practices, burial customs, and monument maintenance show structured behavior with shared meaning. These practices do not map neatly onto modern distinctions between religion, science, and politics. Applying such categories risks misrepresenting how prehistoric communities understood their actions. Archaeological classification systems themselves influence interpretation. Period labels such as Neolithic and Bronze Age are based on dominant tool materials. They do not capture the full range of social or technical variation. Communities using similar tools could differ substantially in organization and practice. Terminology simplifies a record that is inherently diverse. Comparative frameworks introduce additional limits. When prehistoric Britain is compared to contemporaneous societies in the Near East or Mediterranean, differences in writing, urbanization, and state formation dominate discussion. These comparisons can obscure local trajectories. The absence of certain features does not indicate inferiority, but reflects different developmental paths shaped by environment and tradition. The term civilization is particularly problematic. It often implies cities, writing, and centralized governance. Using the term can create false expectations and encourage speculative explanations. Archaeologists increasingly avoid it in favor of descriptive language tied directly to evidence. Advanced carries similar issues. Advancement suggests a linear scale with a defined endpoint. Prehistoric societies did not develop toward a single model. Their achievements must be evaluated within their own contexts. The monument reflects success in coordination, durability, and knowledge transmission, not progression toward modern institutions. Scholarly language has shifted accordingly. Recent research emphasizes capability rather than rank. Terms such as skilled, organized, and technically proficient are preferred because they describe observable traits. These descriptors avoid implying unmeasured attributes. Public discussion often lags behind academic caution. Popular accounts may frame the builders as mysteriously advanced or unusually primitive. Both extremes distort the evidence. The archaeological record supports neither hidden, lost civilizations nor simple, unsophisticated communities. Clarifying terminology is therefore part of interpretation. How researchers describe the builders shapes how evidence is understood. Precision in language reduces the need for speculation. It anchors discussion in material fact rather than assumption. The monument's construction demonstrates that complexity does not require writing, cities, or metal tools. It also shows that technological simplicity does not preclude long-term planning. These observations challenge modern hierarchies of development. Understanding advancement in this context requires abandoning linear models. Instead, it involves recognizing multiple forms of competence. Coordination, memory, and adaptation were as critical as material innovation. Archaeological evidence allows assessment of what was done, how it was done, and over what time span. It does not support assigning value judgments based on modern standards. The builders achieved outcomes appropriate to their circumstances. Terminology remains a tool rather than a conclusion. Its use must be adjusted as evidence changes. In this way, language itself becomes part of the scholarly process. Subject to revision, the question of advancement thus remains open-ended. It frames inquiry rather than resolving it. Careful description replaces broad labels. The material record guides interpretation without requiring speculative classification. What the evidence can and cannot support, archaeological interpretation, depends on material that survives and on methods used to analyze it. At this site, Stone, bone, pottery, soil layers, and tool marks form the primary dataset. These materials allow reconstruction of sequences, techniques, and patterns of use. They also define clear limits. Certain questions can be addressed with confidence, while others remain unresolved because the evidence does not exist or cannot be recovered. Chronology is one area where evidence is relatively strong. Radiocarbon dating, stratigraphic relationships, and artifact typology establish a framework that places initial earthwork construction around 3000 BC, major stone erection around 2000, 600 2000, 500 BC, and continued activity into the Bronze Age. These dates are supported by multiple independent samples. While individual dates have margins of error, the overall sequence is stable. Construction methods are also well supported. Excavation records document stone holes, packing layers, tool marks, and associated implements. Antler picks, flint hammerstones, and worked stone surfaces provide direct evidence of how digging and shaping were carried out. Experimental archaeology confirms that these tools were capable of producing the observed results. Claims that the monument could not have been built with Neolithic technology are not supported by the material record. Stone sourcing is another area with strong empirical backing. Geochemical and petrographic analyses link sarsens to West Woods and bluestones to specific outcrops in the Preseli Hills. These conclusions are based on measurable properties rather than inference. While precise transport routes cannot be reconstructed fully, the origins of the materials themselves are established within narrow geographic ranges. Patterns of movement and interaction are supported indirectly. Isotopic analysis of human and animal remains demonstrates that individuals and livestock traveled long distances. Genetic studies document population change during later phases. Artifact distributions show exchange of stone, metal, and ornament materials across Britain and beyond. These lines of evidence confirm connectivity but do not specify motives, organization, or social structure in detail. Alignment and orientation evidence is measurable but interpretively constrained. Survey data confirm consistent orientation along a northeast-southwest axis aligned with solstitial events. Secondary alignments and potential lunar references are statistically plausible in some cases. However, orientation alone does not establish function or meaning. The evidence supports intentional alignment but does not specify how such alignments were understood or used. Ritual activity is evident through repeated deposition of bone, pottery, tools, and human remains. Stratigraphic context and dating demonstrate that these practices occurred over extended periods. The selection and placement of materials show patterned behavior. What cannot be recovered is the symbolic framework within which these actions were meaningful. No inscriptions, iconography, or verbal records survive to clarify intent. Social organization remains partially accessible. Evidence supports cooperative labor, seasonal aggregation, and shared technical knowledge. There is no material indication of centralized political authority, written administration, or permanent elite residences. At the same time, absence of such evidence does not prove absence of leadership or hierarchy. Archaeology can identify coordination, but not its precise social mechanisms. Claims of external intervention or lost advanced civilizations are not supported by current evidence. All documented construction techniques, materials, and tools fall within known Neolithic and early Bronze Age practices. No artifacts, materials, or structural features require technologies beyond those attested elsewhere in prehistoric Britain and Europe. Assertions of unknown external builders extend beyond what the data can substantiate. Likewise, claims that the monument served a single exclusive purpose are not supported. The evidence shows overlapping functions: construction, burial, observation, gathering, and deposition occurred in the same landscape across different periods. Attempts to reduce this complexity to one role oversimplify the record. Preservation bias limits interpretation. Organic materials such as wood, rope, textiles, and foodstuffs rarely survive. Their absence restricts understanding of scaffolding, transport systems, and daily practices. Interpretations of these elements rely on indirect traces and comparison with better preserved sites. Archaeological methods themselves impose limits. Excavation is selective and destructive. Areas left unexcavated may contain relevant information. Earlier excavations did not always meet modern recording standards, creating gaps that cannot be filled retrospectively. New techniques refine understanding but cannot recover what was removed without documentation. Comparative evidence helps contextualize findings, but does not resolve local questions fully. Similar monuments elsewhere show shared traditions, yet each site has distinct sequences. Applying models from one region to another must be done cautiously. General patterns do not substitute for site-specific data. Language also constrains interpretation. Terms such as ritual, ceremonial, or symbolic describe observable patterning rather than internal belief. They are placeholders for unknown meanings. Using them does not imply uniform understanding among past participants. The evidence supports sustained human engagement over centuries. It supports technical competence, planning, and memory without writing. It supports long-distance interaction and adaptation across population change. It does not support precise attribution of purpose, belief, or social hierarchy. What remains is a record of actions rather than explanations. Stones were quarried, moved, shaped, erected, adjusted, and reused. People gathered, worked, ate, deposited materials, and buried their dead. These activities are visible in the archaeological record. The reasons behind them are only partially accessible. Responsible interpretation requires maintaining this distinction. Evidence can describe processes and sequences. It cannot supply intention where no trace remains. Where data end, interpretation must stop. The monument therefore stands as a documented product of known human capabilities operating within prehistoric contexts. Its construction does not require unknown technologies or undocumented civilizations. Its meaning cannot be reduced to a single explanation. The boundary between evidence and speculation defines modern understanding. Staying within that boundary preserves reliability. Crossing it replaces data with assumption. What archaeology provides is constraint. Within those constraints, multiple interpretations remain possible. Beyond them, claims lose support. The record preserved in stone and soil continues to guide inquiry. New methods may refine details, but fundamental limits remain. Understanding is shaped as much by what cannot be known as by what can. The evidence establishes achievement without requiring exaggeration. It documents continuity without invoking mystery. It defines a complex past that remains partially open, bounded by material fact rather than narrative completion.